Have you ever pondered the inner workings of Kohonen self-organizing feature maps? Today, we'll dive deep into the training algorithm of this fascinating artificial neural network used for unsupervised learning and lay bare its inner mechanisms. First up, we have the initialization phase. A Kohonen map is essentially a grid of nodes or neurons, each linked to a weight vector that matches the dimension of the input data. The weight vectors could be initialized randomly or using a specific strategy to cover the input space. Output. Next, we engage in competition. An input vector is presented to the network. The algorithm then calculates the distance, commonly Euclidean, between the input vector and the weight vectors of all neurons. The neuron with the weight vector that's closest to the input vector is crowned the best matching unit, or BMU. We then transition to cooperation. A neighborhood function, often a Gaussian or Mexican hat function, is defined around the BMU. This function determines the neighborhood radius that will be affected by the learning process around the BMU. The weights of neurons within the BMU's neighborhood get adjusted to resemble the input vector more closely. The adjustment magnitude decreases with distance from the BMU, as determined by the neighborhood function. Adaptation follows. A learning rate parameter controls the degree of weight modification. The learning rate typically decreases over time according to a predefined schedule. The weight of the BMU and its neighbors get updated to become more similar to the input vector. The update is proportional to the distance from the BMU and the learning rate. The process repeats in the iteration stage. All or a subset of the input vectors are presented in each iteration. Over time, the network adapts its weights so similar input vectors are mapped to neurons that are close to each other on the grid, thereby preserving the topological properties of the input space. Finally, we reach convergence. The algorithm converges when changes in the weight vectors become negligible or after a predefined number of iterations. The learning rate and the neighborhood radius are typically reduced over time to fine-tune the map's adaptation and allow it to stabilize. The resulting Kohonen map reflects the distribution and relationships within the input data, with similar data points represented by adjacent neurons on the map. The map can be used for visualization, clustering, and dimensionality reduction tasks. In summary, the training algorithm for Kohonen self-organizing feature maps involves initializing the network, iteratively finding the BMU for each input, adjusting the weights of the BMU and its neighbors to become more similar to the input vector, and gradually decreasing the learning rate and neighborhood size until the map converges. This process organizes the high-dimensional input data into a two-dimensional representation that preserves the topological properties of the input space. Now, isn't that something to marvel at?